Okay, in this last video of intro, we're going to take what we did in the last video, which was the trig of the initial velocity vector, and apply it to a diagram and just kind of map out what is happening during projectile motion. The things we need to remember about this from the first video is that that initial velocity in the x direction, that is constant. So you have a constant velocity in the x direction. Remember, like think dot diagrams for now. All the dots are the same distance apart. And then the y velocity has an acceleration attached to it. So that's your initial y velocity. That velocity will start to change as soon as the object gets into the air. And the vertical velocity of the projectile is going to change at a regular rate according to negative 9.81 meters per second squared. So I'm going to try and apply this to this diagram here. The path that a projectile takes is parabolic, and that is because the position, horizontal position, changes at a regular interval, whereas the vertical position depends on the square of the time. So for those of you who have already learned like parametric equations, this is the example from physics on how to apply them, where you have two variables that change according to a third variable. Basically, both the x and the y position change according to time. The change is linear with respect to the x direction, but quadratic with respect to the y direction. So all projectiles follow a parabolic path, and so I'm going to approximate that here. Okay, so we'll say that that is the path that this projectile will take. It's called the trajectory. And you'll see that like as soon as it leaves, this arrow is pointed in a certain direction. The path of the projectile is always more shallow than that. And so we're going to stop at 5 places on this diagram. It's going to land here because we're going to imagine it's a flat ground. We're going to imagine the highest point of this ball that gets kicked, and then also 2 points that are like somewhat evenly spaced in between. And so what I want you to notice is if I took all of these images of the ball and dropped them down, if I did a good job, they would be approximately the same distance apart. So these distances would all be the same because in the x direction, the motion is constant. Obviously, in the y direction, that isn't true. Height-wise, these two are kind of far apart, and these two are closer together. These two are the same height-ish, and then this one is the same height as that one. So the path is parabolic. It climbs rapidly at first, and then has a more shallow trajectory, and then as it falls, it declines faster as it goes. We can use arrows to represent the vectors. So if I choose, let's say, blue for the horizontal velocity, that horizontal velocity is constant. And so as this thing travels, we imagine that it has the same horizontal velocity as at every moment in its trajectory. So I'm going to attempt to draw 5 velocity arrows that are the same length. The horizontal velocity never changes. It always points perfectly horizontal. And the idea is when you kick something, it's just going to keep moving in that direction. So that horizontal velocity is constant. Because of things like drag, it's going to slow itself down a little bit, but it's going to maintain mostly that same horizontal velocity. Vertical velocity is not constant. So hopefully the red marker shows up okay. We're going to track vertical velocity with the red marker. It starts with some value. And so when you kick this ball at an angle, it moves horizontally and it starts to move vertically also. So we will have Vy, that's the initial velocity, be a large arrow pointing up. Because of what we know about vertical acceleration, if this is positive and this is negative, then as soon as the object gets into the air, the vertical velocity is going to decrease, right? This was some number that's determined by how hard you kick the ball. This is some number that's determined by the Earth, basically. And as soon as it gets into the air, this term is going to reduce the velocity. And so what happens a certain amount of time later is the vertical velocity is smaller. So this vertical velocity decreases as the object rises. Something very special happens here. This is the peak of the trajectory, or the highest point of the trajectory, and you'll notice that the curve is flat there. There's no arrow for vertical velocity here, because this is the magical moment where it is done moving up and it is about to start moving down. So the top of an object's the top of a projectile's path is defined as the moment when its vertical velocity is equal to 0. It's still moving because it's moving in the horizontal direction, but it's just not moving up or down right now. Then the projectile starts to fall, and so that vertical arrow that was pointed up has now been overcome by acceleration, and so it's now pointed down. Because these two pictures of the ball are at about the same height, these arrows should be the same length as one another, but in opposite directions, meaning the vertical velocity is like some positive value here, and it is the same value but negative there. So this is a symmetrical trajectory. So anytime you have, like, before the peak at some height and then after the peak at the same height, those velocities are the same magnitude, but just opposite in direction. When you finally get down to the ground, you actually have the same vertical velocity again, but now it is directed down into the ground. So, the ball's going to hit the ground and bounce. And so it has to be moving forward still. It also has to be moving downward when it strikes. So when you establish the initial velocity vectors of a projectile, you remember the horizontal one doesn't change, but the vertical one always gets more and more negative as the object travels through its path. So before we get to any practice problems, just taking a look at the trig that we do most of the time, and then the way that the path of the projectile is influenced by the acceleration or lack of acceleration. And so next one, we'll get into some problems.